Great. So I was saying this talk is kind of related to one that Alicia gave on convolutional neural networks, and hope you understand why really soon. And it has been prepared together with Carlos Ventura, that he, maybe you want to say hi as you are already there, Carlos?
Yeah, of course. Hi, everyone. Yeah, I will just doing the tutorial, the hands-on after the Xavier's presentation.
Yeah, great. So, but actually, like many of these slides, actually, they were prepared by Carlos, so you can think it's a joint presentation. So the goal of this talk is that given the tools that you have been introduced to on deep learning, how we can address one task which is called image segmentation. We'll have like this talk from him, the introductory lecture. Then you'll have like some hands-on with Carlos. And actually later you have one lecture which kind of digs into the applications of image segmentation for medical analysis, which is one of these fields in which these, let's see, neutral technologies have more applications. So let's move forward. First, I'm an associate professor at the University of UPC University. It's called the Technical University of Catalonia in Barcelona. And here you have like my contact email in case you wanna reach me later, or also I invite you to follow me on Twitter, right? So I teach this at UPC quite a bunch of courses on deep learning now. We have been teaching a lot on that topic since 2015. And I'm also a visiting researcher at the Barcelona Supercomputing Center. Hopefully, at this point, you are all aware that in order to have these magic deep neural networks work, it's important to have powerful computations, it's important to have GPUs, and that kind of motivates somehow my affiliation to this high-performance computation center. So in the past, I was in Brussels, in VUB. I worked at Sony for a year. I've been visiting Columbia University also a few times. First, before I jump into the topic, I would like also to explain that Barcelona, maybe it's not known so far yet for deep learning, but actually we have like quite a strong tradition of researchers who have been educated in Barcelona. Now they are like kind of big stars on this deep learning field, people like Oriol Vinyals or Antonio Torralba or Laura Leal. And as we have like these very powerful researchers who are abroad or in-house on deep learning, since 2018, we organized this deep learning symposium at Christmas time, in which we all share experiences. You can check the videos from 2018 are there, and you'll find like lots of nice talks there, especially if you're interested in the area or investing in our country or just coming to study. And hopefully soon we'll have like the videos from 2019, where we had Oriol Vinyals from Google DeepMind last year as a keynote speaker. And we are already planning for this year edition, which will be, that's always at the end of the year, just before Christmas time. And it all indicates it's going to be virtual. So probably we're going to follow a similar path as this summer school and make it for a global audience. If you want to learn more beyond this school, I invite you to check all our teaching material courses we have online. We have quite an impressive and big catalog of courses, of slides, video lectures that cover different aspects of deep learning. One of them is vision, and which is the one that's kind of related to this talk. But there are also like courses which are like more generic, like maybe the ones we had on the first day and a half of this course. We also have people who are working on speech, on natural language. Now we also started a course on deep learning for reinforcement learning. So we're kind of covering actually like mostly the same areas that have been briefly introduced in this excellent summer virtual school that we are all attending. So you can, on the slides, you can click on all the years and will access the videos. And in case you want to follow like more regulated education, we also have an online program that we are launching this November with researchers. Most of us were in Barcelona, but some of them, they are abroad. As I mentioned, some of them will be in New York, I think in Munich, somewhere else. It's a postgraduate course that it's really oriented for people to industry. So there's a lot of hands-on there to learn Python. And Carlos and me are one of these instructors. Okay, I think that's all for the promotion on why explain why I'm here. Just also to say that both Carlos and me will acknowledge like previous instructors or PhD students who have been teaching this course this lecture we start now. You have the videos there in case you want to see it explained in a different way. Let's start with the topic. I remind you that the topic of this talk is Introduction to Image Segmentation, and the first thing we need to do is to define what's the problem we are trying to tackle, right? So far, you should have been familiar with the problem of at least image classification, which means that given, let's say, an image, we want to label, want to classify that image. In this case, you have this image on the left. It says you would like to have a neural network that the output will say, in this image, there's a chair and there's a bin. And that's, I think you have seen these kind of basic applications, because that's the basic toy example, not even toy, but the benchmarking that most people are working in many machine learning applications, especially using the ImageNet data set. But in this talk, in this lecture, this model Carlos and me are having, we're going beyond that. We are going from a global scale, which is the full image, into a more local scale. Maybe you have seen somewhere else, this is other application, the one in the middle, that's called object detection, okay? The task of object detection is a well-defined task for computer vision, and what refers is now, the goal is not just to generate a label for the whole image, but I want to predict the coordinates of a bounding box surrounding the object, as well as the label, right? So we want some rough localization of where the object is located. This will be the chair, and this will be the bin. On the other hand, the task that we are addressing in this lecture, it's the one on the right, image segmentation, which means that now what we want to do is also to predict labels, but not for the whole image, not for a bounding box, but for each specific pixel on the image. So in this case, in blue, you have labeled the pixels that correspond to the chair. You have labeled in green, painted in green, which would indicate green labels, the pixels that correspond to the bin. So this is a task, so we are going to address the task on the right. So in more general, the goal, our task will be to try to define the accurate boundaries of objects in an image that predict a class map for each pixel. And now I will develop a bit more on this, but that's kind of the goal that we are trying. We would like to have neural networks that can solve these kind of problems that you see, that you could draw the boundaries of the puppies and the dog and the cats that you see. Why is that important? So there are plenty of applications for image segmentation. One that is capturing a lot of attention is autonomous driving, so that cars are aware of what's around them. And one way to do that is to label the pixels of the cameras that are sensing the aura around them. Other application that's going to be the next model later, and there are plenty of them, it's medical imaging. Doctors, they do a lot of diagnose based on medical imaging, and analyzing these images is very hard, it's very tough, it can be exhausting for humans, and in this sense, computers can help and assist a lot in diagnosing, and you see later lots of applications for that. In that case, the classical problem is just to localize some pixels that maybe they might contain a tumor, or maybe there's some small damage that you want to treat. There are also applications for robotics. Again, robots, normally people doing robots, historically they have focused a lot on the control part of the robot, but now thanks to the advances in vision, now it's really, you can put everything together. You can connect the control task with the vision task, everything together with deep neural networks. I think that you have already had lectures on reinforcement learning, and that's very exciting. But still, like the perceptual and control tasks, they can be trained at least separately if necessary. Or things like scene understanding, maybe you want to plan how to, like furniture for your room, and you want, that's on. Try to figure out where you left your phone or your keys at home. That's a kind of things that might benefiting of having a good computer vision solutions that can localize in detail the pixels. So based on this general framework, let's start this diagram of my chalk. You'll see that there are like two big parts. One that's called semantic segmentation, and the one that's called insect segmentation. These are the two parts that are central for my chalk. I will first start discussing kind of a toy case, but I think it's important so that we are all get familiar with the problems and challenges that we are facing. And in the end, I will briefly introduce another task, which is called panoptic segmentation, that you'll understand perfectly after seeing semantic and insect segmentation. So all of them, they are different flavors of image segmentation tasks. Let's start from the beginning row, from global to local scale image classification, and what I mean with that. Here in this slide, I'm trying to show you what's the problem that we are trying to solve. On the left, you have an image, still image of a lady, and what we would like to solve is what you see on the right. Maybe that's not so nice visually. For humans, it's harder to understand, but that's what, let's say, what the computer sees, right? What the machine will see. What we like to have is assign a label. In this case, labels correspond to person, purse, plants, grass, sidewalk, building structures, and align each label with ideally each pixel. You'll see that now you'll see that our first iteration will not solve pixels, but almost there. But let's say that like at a very local scale, figure out what's the class that it's present there. Yeah, so it's solving a classification problem, but at a local scale. And I know I'm insisting a lot on that, but that's central for all this lecture. Okay, so now we're going to call that we have going to have like different semantic labels. When I say semantic, I mean to the semantic class, like person, purse, plants, grass, and that's what we would like to achieve. So the first thing that normally deep neural networks we struggle is how to represent information. So far, you have already seen how to represent the image on the left, right? So you have seen that images in the end, you can represent them or encode them as 3 channels RGB, for example, and that encodes the visual information. Maybe it's not that obvious how to let a network encode the semantic labels, the result of the segmentation task that we are trying to solve. So far, what you have seen in image segmentation, at least, sorry, in image classification, at least, is that when you have a semantic class, you can encode each class with a one-hot encoder, one-hot encoding, which means that if I have like 1,000 classes as an ImageNet, I'm going to have all these zeros across all the vector, and one of the positions is going to be a 1, right? And that's how, depending on the position where the 1 is located, that represents, in this case, the person, the purse, the plants, the sidewalk, so the semantic class. What if we're trying to solve a segmentation task? How are we going to have the labels for each pixel? That's not that obvious, right? Because we have like so many pixels in the image. We don't have not enough with one hot encoding. I think that this representation solves our problem, which kind of, as you see, what it defines is different channel, let's call it channel, okay, for each different class. And then you can think that each of the channels, like you have a channel for person, have a channel for purse, channel for plants, sidewalk, building structures. Each of them, now we use zeros or ones, kind of a hot encoding dish, to say whether that class is present, is aligned with the corresponding pixels, let's say. If we have networks that at their output, they can generate this type of tensors, this type of 3D structures, then we are going to have deep neural networks that can solve the image segmentation task. Okay, and always that's kind of specific or novel for you, because I don't think I've seen any charts so far that kind of uses this kind of representation. Yeah. So again, our input is going to be like in the most simple case, 3 channels RGB. The output is going to be a tensor with the spatial dimensions, width and height, ideally with the same dimension, the same spatial dimensions of the input image, and as many channels as semantic classes we want to label, as many different labels we have to predict. Let's proceed. So Okay, so now we know what we expect to have at the output. Let's see how we can solve it. The first option you can think about, it's a very naive approach, and it has a big drawback, but it's possible to do that. You could say, okay, I'm going to do is I'm going to take my image from all my training set. I'm going to start defining many patches. So these like crops over the image, but many of them all around the image. I will need, we are thinking about a supervised segmentation setup, which means that when I do my training, I will have my annotations. It means that on my training data set, I will have RGB images, and also for each image, somebody will have annotated the image. So you will have labeled each pixel, whether it's a cow or it's grass, okay? We assume that we have this for training in this, for this lecture. Then we will have both for each patch. I can look at the sensor of the patch and say, okay, this patch corresponds to cow. And then I would be able to generate a huge amount of patches, each of them with a label, train a convolutional neural network, the ones you already know about, though. Any your favorite ImageNet architecture. I mean, maybe I hope you've heard about AlexNet, or maybe it's something more recent like a MobileNet or ResNet, whatever. One architecture that has been successful for classification, the convolutional network. You train that, and then at prediction time, at test time, what you do is, again, you have a new image, you take patches of the image, you feed it through the network you have trained, and at the center, and then you classify the center pixel of each window. And if you slide this window over the input image, in the end, you have a solution for the image segmentation task that we are trying to tackle. That's something you can do, okay? This is a really bad idea, actually, but it's easy, but it's a really bad idea because it's so demanding from a computational perspective, right? Because for each pixel, you will need to feed one image crop to the network, and that's going to take a huge amount of time. It's not the best option we can think about. So one first approach to solve that, which is the first one that I want to introduce, and it's more for you understanding what's going on. It's not the best solution, but it's interesting to understand what's going on. It's what we call that we convolutionize a neural net, a CNN, a convolutional neural network. What does it mean? It means that we're going to take a CNN trained for image classification, so for the whole image, and we're going to make some changes there so that we can feed the whole image in there, and in a single pass, it will predict the labels for all the pixels. How we do that? If you remember some of the classic, let's say at least, convolutional networks, many of them, and I know that not all of them, but at least the first ones that appear, what they had is they had like some convolutional layers at the beginning, and at the deepest ones, they had what we call fully connected layers, or like the regular multilayer perceptron. So you have neurons which are connecting with all of them, so they don't have these convolutional filters. And this combination, it's the one that won the ImageNet challenge in 2012 and started all this deep learning revolution. So the problem of these networks is that what they do is they predict at the output, they predict like kind of confidences for different classes. And now the question is like, how could we use a network that it's pre-trained for image classification to solve this segmentation task? So the way to do this convolutionization, I guess, that we should call it, it's to think about the neurons in a fully connected layer as if they were convolutional filters. So how to understand that? Imagine that you have one neuron of a fully connected layer. In this case, there are only two neurons in this layer. That the input, in this case, it's an RGB image, just to make it easier, of only 2 per 2. And then each neuron, it's connected to all of the 4 per 3, so 12 input pixels, right? You could, so you can think about this a neuron fully connected layer, but you could also think, reformulate it in a same way that this actually, it's this neuron corresponds to a convolutional filter of this size, three channels and 2 per 2, okay? So then what I'm doing, but I'm just changing the definition, is something you can encode very easily, and just saying that now this person doesn't need, I mean, it will expect this 12 input data tensor, but when I make it convolutional, I can move it around. I can make it as convolutional filters. They are invariant translations. I can move it around the input data. If we do that, and we have a neural network that I have trained for image classification, so for given as an image, a small image, okay, and I define, when I say define it, it's just that same parameters that I learned, I just change the definition on PyTorch or in TensorFlow and whatever, and say, okay, now this linear layer, this fully connected layer, it's a convolutional one. I convolutionize it. Now, if I fit a larger image, the output will be also larger and will actually predict like local predictions. That's what I was talking about, global and local scale classifications. Now, in this case, I would predict a heat map. So it means like a local prediction for each different, it's not exactly a pixel, but it's something more local than not just the whole image. And that can give us an idea of more or less where the cat is predicted, is located. So it's great because if we do that, we can fit the whole image at once, and we're going to have local predictions of where the cats or the cows or the grass are. Like, for example, we ran this in our university. We had a model that was predicting if a sentiment of the image, if the image produced positive or negative sentiments to humans. And now, by doing this trick, we could have on the row below, you can see like local predictions of positive or negative sentiments with a network that was trained at the image level, at image level labels we had, right? But we had here below, you see like local predictions. This is not exactly semantic segmentation, but it's getting closer to where we want to go. Why is that? Because actually, as in most convolutional networks, there are these pooling layers that that Alicia introduced. That actually makes that if the input, it has some spatial resolution, and there are some pooling layers in the network, the spatial dimension of the tensors will be reduced. So every time there's a pooling, spatial pooling, the spatial dimensions are reduced. So this means that it's impossible, like if we only do what I just presented, that the number of pixels that we have the input match with the number of pixel-wise predictions at the output. We'll need to do something else because we obtain some rough localizations, but actually to solve segmentation, we want like a one-to-one relation between pixels and outputs. Okay, so that's as I mentioned, that was like a first step so that you start getting familiar of the kind of challenges that we are facing, but this is not a very good solution by itself to solve segmentation. But it can be a step in the right direction. And I will develop this a bit more. So now we can jump into the core of the talk, which are the two main tasks in the image segmentation field, which are slightly different. One of them is called semantic segmentation here in bold, and the other one is called instant segmentation. So now what I will do is I will introduce what's the difference between semantic and instant segmentation. And then later I will go through semantic segmentation, introduce some concepts, and then instant segmentation, introduce some other concepts. Okay, but first I want you to make a difference, that you understand the difference between semantic and instant segmentation. So when we talk about semantic segmentation, the task that we are trying to solve addresses labeling every pixel. And typically what you do is you assign a class label to each pixel. This means that, for example, in the case of the cows, that if we label each pixel with the class cow, so in the task of semantic segmentation, there is no way to make a difference between the different cows that appear on this image. Okay, so everything is blue. Yeah, everything is blue. It's just cow or grass. That's all. But in semantic segmentation, you don't have the information of how many cows are there in the image. This is just a level-wise pixels. On the other hand, the other task in segmentation does take that into account. In instance segmentation, what our goal is first to detect the instances. We can, maybe you want to say that it's objects. So we want to detect which objects appear in the image. Typically, these are the objects. We assign the category. So we say that's in this case, this is a person, this is a person, this is a person. So we assign the category, the class, semantic class. And also we label the pixels that correspond to each of the instances. In this task, in instance segmentation though, notice what is interesting is the black area. That there are so many pixels which are not labeled because they don't contain any of the objects of any of the instances. Okay. So instance segmentation actually what does you kind of detect and segment the objects. You can think about it the other way, in this way. Okay. The tasks, they are related. In both cases, we are generating label-wise pixels, but again, in semantic segmentation, all pixels are labeled. Everything is painted in blue or green. But there's no way to differentiate between different instances of the objects of the same class. While on instance segmentation, we may have pixels which are not labeled, but there is a way to differentiate instances from the same class. Okay, and then there's a lot of words that it's important that you know which of the two tasks you are trying to address. So remember, semantic segmentation and instance segmentation. Now I will focus on solutions in the literature that have addressed the task of semantic segmentation and have provided some interesting insights that might be useful if you are ever trying to run or reproduce or design one of these models. So let's start with semantic segmentation. Again, I'm just repeating the same, but our goal is to have, if our input has height and weight, so this height is width and 3 RGB channels, we're going to have predictions of height and weight, and actually like as many, there's another, let's say, sorry, it's here. You have the channels here, the C here that you see, that you find here is the amount of categories that we are going to address in the channel. So we have a neural network that will predict that tensor that I showed earlier. And maybe at the end, if you want to assign like only one label for each pixel, you will take the maximum of the different confidences across classes, and you will have this kind of nice colored figure. Okay. Let's return where I left it a few minutes ago when I said, okay, one way to solve something similar to semantic segmentation is to convolutionize a convolutional network that has been already trained for image classification. Which just, in the end, it means that we have an architecture that everything is convolutional. So if we make put a larger image at the input, the output is going to be larger, so it's going to give us kind of local information of the labels that are being predicted. Remember that I said that so this is not solving semantic segmentation because in general, convolutional networks include pooling layers that decrease the spatial resolution. Okay? And there are some exotic architectures that don't do that, but the most successful ones, they do that. So what do we need to do? So actually, this a figure taken from one of these works that I will be citing quite frequently, which actually that's where they introduce this convolutionization to solve the semantic segmentation problem. So, but they did have this limitation that when they feed the image through the network, the output was of lower spatial dimension. I mean, one way to solve that is to do something just to rescale. So if you have a small prediction in space of the labels, you do some upsampling. So this can be something as simple maybe it's not a very good idea, but you can do just a linear interpolation and you just make things, the small resolution image that you have, you just make it larger. Maybe that's not the best thing to do, but it's going to give you something. It will give you a solution, right? There is, well, you can do that. You could do some upsampling in a linear manner, but you'll see that there are other ways to do it which are a bit better. So if you were paying attention to Alicia's talk and you could follow it all, actually, she already introduced a solution for this problem. I mean, when we are trying to upscale the spatial dimensions, the spatial dimensions of our features, of our convolutional features, there's this operations which is called transpose convolution that actually allows that. So I'm not sure how much in detail she explained that, but I will just provide a quick overview on that, okay, and what transpose convolutions are. So just as a refresh, because probably that's something you have done, I'm going to show first what's a traditional convolutional 2D, okay? So we have one input 4x4, and what we do is we run a convolutional filter, okay? And the output of this red filter goes into this position. Then I shift the convolutional filter, and the next dot product, let's say, it goes into this other position. If we are considering stride 1 and path 1, I think that you have worked on this quite a lot. If I have stride 2, what I do is that every time that I shift my filter, I move it 2 positions. Okay, so 1 and 2. And now, let's see, that's the kind of outputs. Just notice that now the output is smaller because I'm just moving the convolutional filter in a larger stride. So now I have an output of 2x2, while earlier the output was 4x4. Let's do now the transpose convolution or deconvolution, which is the operation that we are interested in. Remember that our problem is that we want to upscale the spatial dimensions of our features. So now what we would like to have an input, let's say, of 2x2, and let's see how can we have an output of 4x4. If we keep working with 3x3 deconvolutional filters, we put our, so there are some weights. So the filter has some weights, some parameters that are learned with backpropagation, like the same weight as any convolutional filter, right? But now the weights of this convolutional filter are scaled, are multiplied by the value of the input tensor. And the output, it's going to be located over here. Should have painted it, but it should be giving the value that you put here. Later, now, if what I do is I move one position, the blue, the 3x3 deconvolutional. Now I will have another output. So this blue filter will be scaled again and weighted by this value, and that another value will be located here. So I will be covering the whole area, right? I will be filling all the pixels or all the activation, the features which are below the red and blue. And in this case, they will overlap, but there's no problem. If they overlap, what I will do is I will sum the overlaps. And that's how if you run these operations and you estimate the parameters for your deconvolutional filters, they are going to be optimized to solve this problem. So that was an approach that was suggested in this work, in which, as you see, at first you have, if you want to solve a segmentation task, first you have a convolutional network, and then later, so there's a bottleneck, we call it bottleneck, so actually it really goes to something very small in terms of spatial definition, and now we are doing a deconvolutional network. So this unpooling, it's like, so unpooling, it's kind of the, so unpooling and convolutional filters, it's kind of the transpose convolution in the end. And this way, we have that the spatial, we can recover the spatial resolution of the input and the output, which is what we wanted. There is a problem with this approach, actually. So with this approach, there's a problem, which is that maybe you are aware that when you train a convolutional neural network for a semantic task like image classification, the deeper you go into the network, so the closer you are to the semantic label, those filters and those features, they are more specialized in the final task, in image classification, let's say. But remember that we are trying to solve a task which is called image segmentation. And it's true that for image segmentation, we need to predict the label, semantic label. So it's great that we take activations from the deep, from the deep parts of the convolutional neural network. But we are also interested in the boundaries. And the boundaries of the objects, these are small details which will be lost actually when we go deeper into the convolutional network. So it's very difficult that only by looking at the information that you have here, in which you have applied different pooling operations, which are, let's see, destroying the small details. Later in the end, you have the potential to reconstruct these details, because in the end you were kind of destroying them. Meanwhile, I mean, of course, everything is learned and there's a potential, but you are making things really, really hard for the network. So you are trying to find boundaries with features that are designed or engineered to detect semantics, like faces, but they are not optimized to detect like small edges or the orientation of the edges. So what can we do to solve that? In order to solve that, the trick here is that if we have our input image and at the output, and we have a convolutional neural network, so with our convolutions and our poolings and our output, maybe there's we have some, so there's an output, and in this case they were doing an upsampling of 32 times. Okay, so in this example that I'm showing, there is no deconvolutions. Okay, so in this example, actually, if you see the citation, it's the one that they at that point they were not proposed the deconvolution. So it was just redoing the poolings and trying to solve the semantic segmentation task. So this special definition here is 32 times smaller than the input one. And you can train on your network with that, okay? But that's the kind of results that you obtain. Because it's, so you do the upscaling, you take back to the original resolution, but you see it's not precise at all. It's too coarse. So what they did is that actually they were trying to predict segmentation mask, so the segmentation, the output, segmentation, not only with this, with the features here, but also with the features, with these intermediate features on this layer, on this other layer. And they were combining all the features. Actually, they were doing some kind of combination. So that at the end, by combining the features at the deepest part of the layer, intermediate and a little bit less intermediate, the result was much better. Okay, and we're going to call this skip connections, because you allow some features to skip, so that the features that you compute here and you just take directly to the output, they will not go through all this part of the network. Or the net features that you take here and you take them just directly to the output, they will not go through all these filters or pooling operations. This concept actually, it was later used to design one of the most influential neural networks in medical imaging and in segmentation in general, which is called the UNet, in which now we are doing skipping. So we are taking features here and let's say copying them to the upscaling branch. So here, so the network now it's decreasing the spatial resolution. This will be the bottleneck, and now it's upscaling. And you see here, maybe you don't see, but in white, what it's telling you, these white rectangles, it's telling you that these features that you have here, you are copying them here on the apps. So this downstream, this convolutional part of the network and the deconvolutional, you're copying, actually you are copying and concatenating them with the features that come from the deconvolutional part. And this allows us, the features here, they contain the small details that we need because they are at the high spatial definition. When we copy them and concatenate them so close to the output of the network, there is the potential, it's much easier for the network to recover the small details, together with all the semantic information that's coming from the branch below. So as this is a central architecture for medical imaging, I will just move forward because probably later it will appear again with your lecture on medical imaging. Cool. So skipping connections, or UNets are interesting. Now I'm going to introduce one more concept that helps in semantic segmentation, which is related to something called receptive field. I'm not sure if somebody has talked about receptive field. I will assume not, so I will just make a brief introduction. So the receptive field of a convolutional neural network, it refers to the part of the input data that is visible to a neuron. And when I mean a part, now maybe I should just think about images. So when I have a convolutional filter that at whatever layer, so the features that this convolutional filter is processing, they are the results of the outputs of other filters and the outputs of other filters. But in the end, at the very beginning, there's an image there. There are some pixels. So a convolutional filter at whatever depth, its responses are related to kind of a receptive field that opens when you go back to the image. And the deeper you go into the network, the more open the receptive field. So the more pixels it sees. Okay. The problem, though, is that with the convolutional neural networks, the receptive field is not, by default, it's not infinite. So we are going to have, it's limited. We're going to have pixel-wise predictions. So we're going to see the convolutional filter at some position. We'll only see one part of the image, not all of it. And this may be very important for segmentation tasks. So knowing where a pixel is with respect to the whole context, that can be very helpful, right? Knowing if maybe you will not predict a pixel of an elephant if everything around it is snow, because it's really red, right? You have never seen an elephant in the snow. So having a wide receptive field, so when your convolutional filter must make a prediction, if you can see larger part of the image, that's probably going to help. This is related, and again, I'll take another slide from Alicia, with what she presented on dilated and atrus convolutions, which are these convolutions with holes. Atrus means like with holes. That actually their goal is to increase the receptive field of the convolutional network as you go deeper into the network. So, and it's great because if you add more layers, so the deeper you go into a neural network, and if you are using dilated or atrus convolution, it's the same, okay? The receptive field grows exponentially. It means like in how you open the beam of the image, the part of the image that that filter at that position sees. But the number of learnable parameters grows linearly. So it's very useful, especially for segmentation tasks. I think Alicia also mentioned that. And here you kind of see on dark blue, you kind of see like the shape of an atrus convolutions and how it's more open than the activation part that you see on green. Okay, so I think these are like all the basic tools that I wanted to introduce. And if you start combining these dilated atrus convolutions with something else, which is called spatial pyramid pooling, which is related, it's not exactly, but it's related to being able to have features from different depth of the network. Then you have, that was the building blocks of popular architecture, which like PSPNet. Okay, just go here, but PSPNet, that's the model that you see there, and solves a segmentation. And very famous, it's DeepLab. There's a whole bunch of different versions of DeepLab. The last one is DeepLab v3, which is very popular on PyTorch, on all these models, which it's combining spatial pyramid polling that I don't have time to explain, this encoder-decoder in the sense of convolutional, deconvolutional, and the atrus convolutions. If you put everything together, results are pretty good at reasonable computational. Okay, I will start the last part. This last part, it's more than the first one, which is instant segmentation. So all the techniques that I presented, they were proposed with semantic segmentation tasks, but they are also useful for instant segmentation. Okay, so they were proposed for the task above, but you will also see them in solutions addressing the task of instant segmentation. Remember that instant segmentation it's again, we want to detect the objects and find the boundaries of the objects. So this field is greatly influenced by another task that I introduced at the beginning, which is called object detection, which remember was drawing bounding boxes around the objects. And it's very related because in object detection, I'm going to talk about so the examples now are on object detection, but it's kind of the similar problem. Remember that segmentation means like I detect the object and now I segment it. As I first need to detect the object, it makes sense that literature has been highly influenced by solutions targeting the object detection task, which is having the bounding box only. So many solutions on object detection, what they have done is they have an image, they do something which is called object proposals, which says, okay, I think that all these bounding boxes, they might correspond to puppies and cats, okay? And then you have many candidates, you rank them, okay, based on some confidence metric. And in the end, what you do is you discard all the candidates that you are not interested. So if you say, okay, so in this example, I found like 2 dogs, but you apply something called non-maximum suppression, which basically means that if you have 2 candidates that overlap a lot of the same class, you just keep the one that has the highest confidence score, that the network is most confident about. And in this case, it would discard this candidate. So it would detect only 1 dog. In the example, it has detected 2 cats, and it would discard this cat because the confidence, this value here, it's lower. It's called the non-maximum suppression. And there are so many solutions there that have based on this, and actually later Carlos will talk about it. If you solve this part of having the object proposal, it means that you already have a bounding box over the image. Then from there, you can extract the mask on the bounding box. But it's kind of these are like 2 stages, right? First, I detect the object, and then I extract the mask. And later, you will be using that in the hands-on with Carlos Ventura. So there have been approaches trying to combine these bounding boxes and mask. That was the first one that was proposed. But I'm very interested in briefly commenting this, but later Carlos will talk more about this. But that's the one that's very similar to what you will be doing. So this is a solution for object detection. So the outputs are bounding boxes. What you have is you encode an image, you have a network that makes proposals, object proposals, and then for each proposal, what you do is you generate class properties for each proposal, right? So what is the class that is shown in this bounding box? But you have kind of another network that addresses this. I think I will let Carlos to explain this better because otherwise I would run out of time. With Carlos, actually, you will be using an approach that's using this scheme, okay? That's called mask-RCNN, which for each of these proposals, it will have generate a feature map of fixed dimensions for which you will predict the class, you will improve the bounding box, and you will also generate the mask, the chair mask as well. Yeah. Okay, I think I will let Carlos, if you need to explain more, I will skip these ones so I don't run out of time. These are results that you can obtain with mask-RCNN, which is a very popular model that you can find in all the libraries. So one of the problems of these proposal-based methods is that if 2 objects are really overlapping a lot, the non-maximum suppression step will remove it. You will need to decide some threshold for the non-maximum suppression. The same pixel can be assigned to multiple instances, and the number of predictions is kind of limited to the number of proposals, which is another parameter which is handcrafted. There are some other object detection solutions which are called a single shot, in which they don't have the proposals, and so people have tried to explore with these single shot proposals. There's one called RetinaNet, and then again you have the bounding box here, and then you generate mask for each of the bounding boxes. And also, just very briefly, in our lab, what we did is So we kind of extended the idea of image classification. So you saw yesterday with Alfredo that there are these networks which are called recurrent neural networks that allow working with sequences. So imagine that in this image, you could process and say, there's a cat, there's the grass, and there's stone here below, but as a sequence of an RNN. And we proposed a solution that was capable of kind of reasoning over the image, because it would say, okay, so I have my image, I predict that there's a bike here, as the smell of the bike, and now that I know that this is a bike, I think that this is a dog, and that's it, and there's nothing else, like the stop word when you are doing translation. So we solved the segmentation task with a recurrent strategy. We were not the first ones, but that's another approach that you can try. Okay, I will just conclude with this idea of monoptic segmentation, which is this third task that I mentioned that I wanted to comment, which in the end, it's as simple as when somebody's talking about monoptic segmentation, it means that it's trying to address both tasks, the semantic and the instance segmentation task. It means that, and you can have networks like this one, that is solving both tasks. You have, so you extract your features with a pyramid or wherever, and then you have what they call a semantic head, in which solves the semantic segmentation task, and the instant head that solves the instant segmentation task. And as everything is trained end-to-end, the network learns to solve both tasks at the same time. Yeah, so I think that will be it from my side. If there are, this is still an active field, so you can check latest words that I have put here from the last year. And if you want to play with that, there are some data sets that we listed here in case you're interested. Yeah, just to conclude, also if you want to know more about our research, I invite you to click on these links and maybe check out what we are doing, and you'll see also that there are like some opportunities for basically public grants to apply for them. If you have good student profile and you are interested in our research, we'll be